In this short video I'm going to talk about earthquake focal mechanisms. So when an earthquake ruptures, we have a specific type of motion associated with a type of fault. So if we take, for instance, a strike-slip fault here, so we've got this right lateral strike-slip fault, and we put a load of seismometers all over the Earth's surface, there will be a particular pattern of motions that those seismometers will pick up. So, so if we take this situation here, we've got this right lateral fault. The fault is striking north-south. Anywhere, so if we think about this fault has moved like that. This bit of crust has moved downwards. This bit of crust has moved upwards. So anywhere in this shaded region in here, the first motions that the seismometer will pick up will be a movement towards the seismometer. So it'll be a compressional first motion. And conversely, anywhere over here in this region in here, the first motions will be away from the seismometer. So it'll be a dilatational first motion. And we can think about that on the other side, on the western side of the fault. Again, anywhere in this shaded region here, we'll have the first motion will be towards the seismometer, so it'll be a compressional first motion. And then anywhere over here, because the block is moving this way, is moving northwards, we'll have the first motion will be away from the seismometer, so it'll be a dilational. Okay. So whether we get compressive or dilatational first motions will depend on where the seismometer is in relation to the focus of that earthquake, where the rupture is, okay, and what the type of motion is on that fault. And this is due to the fact that we have this elastic rebound thing that we're sending as we get this elastic rebound. We're sending waves, and the waves propagating in this way will be a compressive first motion, and the waves going backwards this way will be a dilational first motion. Okay, and the same on this way. There'll be a compressional first motion of the elastic waves going this way, but then there'll be a dilational over this way, and we get this classic pattern. But that's just thinking about it in two dimensions. It's a bit more complicated than that, as we know that these are there are three. This is three-dimensional. Okay. And what's important to note is that we get this. I mean, just in two dimensions, you can see it that we've got this is the fault plane, but we've got this auxiliary plane in here, and that we could get the same patterns of first motion from a fault like this, which is right lateral, or a fault like this, which would be left lateral. So this fault and this auxiliary plane are at 90 degrees to each other, and we couldn't distinguish from the first motions whether that was a right lateral fault striking north-south or a left lateral fault striking east-west. So that's the thing, that there are these two fault planes that can give exactly the same first motion patterns, can give exactly the same type of thing. And you need to use this geology to decide which one is the most sensible. So what we do is this is obviously because it's three dimensions. We use we often use stereo nets to do it. So what we do is we plot the vector. So this is a lower hemisphere stereographic projection looking down on the focus of the earthquake. So we're looking at where this is at the place where the earthquake happened, and we plot on the vector of the ray path to the seismometer that we're interested in. So, for instance, this seismometer ray path to seismometer S1 has gone like this, and it goes through point 1 on our stereo net. Whereas this seismometer 2 over here, the ray path is like this and goes through this point on the stereographic projection. So for every seismometer we have a ray path on here, and then we also have first motion, whether it's a compressive first motion, and we mark that in black, or a dilatational first motion, and we can mark that in white. And so we end up then defining 2 orthogonal planes that fit that data, that separates the compressional and the dilatational first motions. Okay, and we normally shade the compressional first motions dark, and we leave white the dilatational first motions. But there are some misconceptions about beach balls, and people often tell that they from the stress directions. So, for instance, if you see on this thing in here, on this first motion here, they plotted T and P. This is the tensional stress, and this is the compressive stress axis. But this is not necessarily correct. Okay, so that they do not tell you about stress directions. They tell you about displacement. So the strain vectors, okay, strain fields, and you need some theory to go from these displacement fields to get stress directions. But that theory may not always be applicable. Okay, but they're always telling you about displacements. We get different patterns of these beach balls, of these first motion solutions or focal mechanisms for different types of faults. So a strike slip, we get this kind of like a beach ball type effect in here, looking down where we've got these 4 quadrants of the thing. So this is the fault in this case, and so it's a left lateral strike slip fault. And with a thrust, we have the compressional first motions in the middle of the stereo net, and the dilatational first motions on the outside of the stereo net. If you think about it, the compressional first motions are pushing upwards, so we get them in the middle of the stereo net, or downwards in this case. And then with a normal fault, we get compressional first motions on the outside of the stereo net, and dilatational first motions in the middle of the stereo net. Okay. And first focal mechanisms were these kind of beach balls were to use to show that the first motion solutions for transform faults at mid-ocean ridges were opposite shear sense. So for instance, we have here these are right lateral shear senses for all of these earthquakes on here, but the offset of the ridge is left lateral. So it proved the theory of transform faults that was developed by was developed in the 1960s. And this is a poem that was written when I was at a conference in Liverpool about earthquakes, which I thought was quite good. This guy Tony Chestnut wrote it in about 3 minutes whilst we were sat in a pub talking about earthquakes.